Hi there, and welcome back. Today we'll be talking about section 5.2, covariance and correlation. So to begin with, let capital X and capital Y be random variables on a similar sample space capital S. And also let us define a function little h of x comma y. So it's a scalar function of two variables, x and y. Then we can define a new random variable, z, by h of capital X, capital Y. And the way to interpret this is that for a particular outcome of the sample space S corresponds to a measurement capital X and a measurement capital Y. Maybe my sample space S is a set of people from the population, and maybe capital X corresponds to height and capital Y to weight, respectively. Well, you can then define a new random variable, capital Z, to be maybe a function of these two amounts of height and weight. So therefore, every outcome of capital S produces a real number defined by Z, and this therefore gives us a new random variable. So one question is, how do we compute expectation of a function defined, or of a random variable like so, defined in the following way? So in the case that capital X and capital Y are discrete, the expectation of the random variable z, we can see that the random variable z will also be a discrete random variable. So therefore, by definition, this is the sum over all possible little z values that capital Z can take on, and it will be z multiplied by the probability mass function of capital Z evaluated at little z. So this is somewhat unneeded because we don't have to compute the new PMF for capital Z. We can simply use the PMF, or the joint PMF, of x and y. In other words, this turns out to be equal to the sum over all possible x values and the sum over all possible y values of h of xy multiplied by the joint PMF p of xy. So I won't go through and prove this, but we can kind of make sense of it. And the idea is this, is that if we look at all ordered pairs x and y that give us back the resulting value z under this function, we can see that such z values correspond to h of xy. And the probability mass function will be the sum of probabilities x comma y that correspond to such a z value. So this is a sensible thing, but we won't go into details on why this is actually true. So for us, the right-hand side of the equal sign is preferable because we know h, we know our joint PMF, so therefore we can compute this. In the case that capital X and capital Y are continuous, again, by definition, the expectation of z will be from negative infinity to infinity of z multiplied by the PDF of capital Z. But again, without proof, this is the same as the double integral h of xy multiplied by the joint PDF f of xy, and integrating over all of R2. So why this is a nice useful construct for determining the expectation of new random variables defined by old random variables. But we can go a little further here. We can actually use this in 5.2 here to do covariance and correlation. So let's look at the following example. Let's see where this can be useful, or where we're going to see it come up. So let capital X and capital Y be continuous random variables with the following joint PDF. So it's given by this piecewise defined function, and I'll leave it as an exercise for you to actually verify that this is a PDF. In other words, it's positive, and the area, or I'm sorry, the volume underneath this function is equal to 1. Let us also define the new random variable given as follows. So capital Z is given by this function of old random variables. So capital X minus capital Y all squared. And just to see what this corresponds to, this is corresponding to the function h of xy, which is just x minus y squared. So how do we figure these things out? So first off, we can compute the expectation of just the random variable x, because capital X is also a function, or a function of capital X and capital Y. So by our definition of expectation, or our result we should say, this is the integral the double integral of our function here, which is just x, multiplied by the joint PDF just like so. Well, according to our definition of our joint PDF, this reduces to the following. So this can be seen because our joint PDF only has support in the first quadrant, and in fact, just where x is on the interval from 0 to 1 and y is on the interval from 0 to 1. So such an integral reduces to the following. So this is a nice one because we can pull out the 4x and x, giving us the following. 4x squared on the outside, and the inside integral is just the remaining y dy. Doing the inside integral, using standard calculus, or the fundamental theorem of calculus, this is just 1/2 dx. So now we just have this single integral, and again, using the fundamental theorem, this one's very quick to obtain 2/3. So I'll leave the details in between here to yourself. Similarly, we can compute the expectation value of y. So notice I've done two things. One is that, again, we're using the same PDF, so therefore only has support over this region, but also I've switched the order of the integration. So this is helpful because we can see that this is now the same integral as above, where we've just swapped places with the x and the y. So therefore, this must be the same number. It is also equal to 2/3. So finally, the expectation value of z is given by the following. which equates to this. So I should point out that many times we're going to compute expectation of some function of x and y written explicitly like so. So therefore the expectation of this function of x and y is given by the following. And this reduces to the following double integral. So in this case, you can either use integration by parts on the first, you can expand this quadratic of x and y, and integrate this entire double integral, term by term, using procedures as was done above for expectation value of x and y, respectively. Or there's a few other ways to do this one. But in any case, it takes a few steps, and so after doing this double integral, I will not do the details here, but this results in the value 1/9. So therefore, we can take the expectation of not just x and y, but functions of x and y. So an interesting consequence is that we already have a definition for expectation value of x. So let's notice something. We're going to see that these two formulations of expectation of x are the same. So we're claiming that the expectation of the random variable x just like so. Well, since this is just x here, I can pull the x outside of the inside integral. And by definition, this inside integral here, so this double integral results to the following. The inside integral is by definition the marginal PDF of the random variable capital X. So this is just x sub x dx. And to see this, the inside integral again is your variable of integration is y. So therefore y is a dummy variable or variable of integration. So this inside bracketed quantity is an expression of only x. So denoted by f sub capital X of little x. That is the marginal PDF of capital X, or in other words, the PDF of the random variable capital X. So by definition, this is our original definition of expectation value of x. So they actually both do correlate. Similarly, one can show the same by doing the same procedure but with y. Notice here, the idea is to switch the order of integration so you can mimic the above procedure. Produces the same result but with y. So expectation is the same in how we've defined it in terms of joint PDF as opposed to the PDF with respect to x or the PDF with respect to y. So with these things in mind, we can now define the following. The covariance between the random variables capital X and capital Y is given by the following quantity. We denote that by COV with a capital C, so covariance of capital X comma Y is equal to the expectation of the following function of capital X and capital Y. So to emphasize here, or remind ourselves, mu sub x is the expectation of the random variable x. So this is by definition mu sub x. Similarly, the expectation of y is the quantity mu sub y. Both of these values are just numbers. These are just numbers. So this is inside function here is a quadratic of random variables, capital X and capital Y, and these two quantities are just numbers. So what is this equal to? It's equal to two quantities, in fact. In the case that capital X and capital Y are discrete, this will be the following. So when x and y are discrete, we know the expectation of this function of x and y is the associated function of x and y, where we replace capital X and capital Y by little x and little y, and we sum over all possible little x and little y, and of course weight it by its joint PMF. In the case that x and y are continuous, in the case these two random variables are continuous, the expectation of this quantity or this function of capital X and capital Y is given by this double integral. Again, for emphasis, mu sub x and mu sub y are the expectations of capital X and capital Y respectively. So in the next video we'll do computations with this and results with the covariance. But to conclude this video, let's look at what covariance means. So rewriting covariance at the top here, the covariance of x and y looks like the following. So it's the expectation of this quantity. Let's consider the case where capital X and capital Y have a strong positive linear relation. So the correlation between x and y is positive. Such an example would be capital X and capital Y being the height and weight of a particular individual. So as if capital X corresponds to height and y corresponds to weight, we would expect that as the individual gets taller, it is more likely that that individual has a higher weight. So let mu sub x and mu sub y denote the mean of these values correspondingly. The way to interpret this scatter plot is the following. Each point on the scatter plot corresponds to an outcome in our sample space. So you give an outcome in the sample space or an element of the sample space, I will give you back a point. So for example, maybe this point. So underlining this point here. The coordinates of that point has the x coordinate corresponding to its capital X value. So in other words, for that particular outcome, we get a measurement capital X by the random variable capital X. That measurement is the corresponding x coordinate. Similarly, its y coordinate is then the output of the random variable capital Y with that same outcome in the sample space. So every sample in the sample space can think of as corresponding to points on a scatter plot. when we talk about a strong positive linear relationship, it looks like the following. It doesn't fall exactly on a line, on a line with positive slope, but it falls somewhat close to. And so what do we mean by this? Is that let's see if we can draw any conclusions about the covariance. So in this case, if I consider values, let's say, of x that are above mu sub x, if I consider only these values, or the points in the scatter plot, in which the x-coordinate is greater than mu sub x, we can see that most of the points in this region correspond or have y-coordinates that are usually above mu sub y. So if I restrict ourselves to only our points in our scatter plot, in which the x-coordinate is greater than the mean of mu sub x, then most of these points also have a y-coordinate that is corresponding to a value greater than the mean with respect to capital Y. What is this saying? In short, it's saying that large values of capital X correspond to large values of capital Y. Similarly, small values of capital X correspond to small values of capital Y. In conclusion, the covariance of capital X and capital Y, which is just the expectation of this quantity. When x is greater than mu sub x, we expect this quantity here to be positive. In that case, for those such quantities, those such outputs in which this is a positive quantity, we can see by the following scatter plot, this quantity will also be positive. Therefore, the product will be a positive number. In the case that x minus mu sub x is a negative quantity, then the corresponding y-coordinate will on average also be a negative quantity. In other words, points in our scatter plot in which the x-coordinate is less than the mean corresponds to points in which the y-coordinate is also less than the mean. Therefore, the product of a negative and a negative is a positive number. Therefore, we're taking the expectation of an expression that takes on a positive number more often than a negative. Therefore, for when capital X and capital Y have a strong positive linear relation, we will see a covariance that is positive. Similarly, when capital X and capital Y have a strong negative linear relation, you have the reverse effect. In other words, values or outcomes in our sample space in which the x-coordinate is greater than the mean will correspond to points in which the y-coordinate is less than the mean. So therefore, when this underlying quantity here is positive, we can expect this underlying quantity, capital Y minus mu sub y, to be negative. In other words, the inside expression here is a negative number. Similarly, when we consider only points in which the x-coordinate is less than mu sub x, we can expect the y-coordinate to be greater than mu sub y, resulting again, so in the case that this left quantity is negative, we'd expect the right quantity to be positive. In both cases, this product will be a negative number. So therefore, the expected value of this expression, or the covariance of x and y in this case, we can expect to be less than 0 for some amount. Finally, in the case that capital X and capital Y have a weak linear relation, there is no relationship between restricting ourselves to points that are above, have x-coordinate above mu sub x, doesn't tell us anything about what the y-coordinate should be. In other words, the y-coordinate is just as likely to be above mu sub y as it is to be below mu sub y. Similarly, if we talk about points in which the corresponding x value is less than mu sub x, again, the y-coordinate is just as likely to be above mu sub y as it is to be below mu sub y. In other words, if we take the average of these products, this product is just as likely to be positive as it is to be negative. Therefore, in such a case, the covariance of x and y we can expect to be approximately 0. Therefore, covariance tells us something about the positive or negative linear relation between x and y. In the coming videos, we will be doing more computations with covariance and also looking at some of the consequences of covariance and define also correlation.